Okay, so at the end of the last video, we were looking at some important properties of radiation. Specifically, we looked at things like penetrating power and the reactivity of the different types of radiation. In this video here, we're going to be looking at another property that's very important, called the half-life. Now, half-life is a term that is used to describe a lot of different processes. Okay, basically what it is a measure of just how long it's going to take for something to go away. So we can use half-life to talk about things like how long it takes for a drug to be eliminated from somebody's body, or how long it takes for a pesticide to be washed away. In this particular case here, we're going to be talking about how long it takes for half of a sample to decay or decompose. So the half-life is going to be the time needed, or I should say, time needed for 50% of a sample to decay. Okay, so for example, let's say we start off with 100 grams of a radioactive material. Okay, if we let that sit around for one half-life, which I'll symbolize as T1 half, after that first half-life, we'll have 50 grams remaining. If we let it sit around for another half-life, okay, we'll be down to 25 grams. And if we let it sit for one more half-life, you'll be down to 12.5 grams. Okay, and this will just continue on until we get really close to zero, but it would take forever to really get to zero there. So half-life is very useful when we're trying to figure out how long radiation is going to hang around, because we know that radiation is dangerous stuff. We would like to know when a sample becomes safe. In other words, it does not emit a dangerous amount of radiation. Okay, so it turns out that half-lives can take on a very large range of values. Okay, so half-lives can range anywhere from the order of seconds, sometimes even shorter than that, all the way up to hundreds of billions of years. Okay, so let's say we were to be given a problem here, and let's say the problem says that we have 16 grams of a substance, a radioactive substance. So 16 grams of a radioactive substance has a half-life of, we'll say, 20 minutes. Okay, how much of that substance will remain after 2 hours? Okay, so the first thing we need to do is we need to take those 2 hours and figure out how many minutes that is. Okay, we know there are 60 minutes in 1 hour, and that'll give us 120 minutes. Okay, now with a half-life of 20 minutes, we can take that 120 divided by that half-life, and we find that a total of 6 half-lives are going to pass. So let's think about this. We start off with 16 grams. Okay, after the first 20 minutes, we're down to 8 grams. After the next 20 minutes, we're down to 4. After the next 20 minutes, we're down to 2 grams. Now, so we have our first half-life, our second half-life, our third half-life, and we need to get to 6. So we're going to continue going here. Okay, so we have another 20 minutes pass for our fourth half-life. That gets us down to 1 gram. Another 20 minutes. That'll be our fifth half-life. Gets us down to 0.5 grams. And then another 20 minutes will be our sixth half-life, and that gets us down to 0.25 grams. Okay, so after 2 hours, we would have had a total of 6 half-lives pass. So that 16 grams goes down to 0.25 grams. Now that's with a 20-minute half-life. Now, can you imagine something that has a longer half-life? Things like radioactive carbon, carbon-14, are going to have half-lives on the orders of thousands of years. Okay, uranium, which is a very important isotope for us to recognize. This is the stuff that's used in nuclear power, and it's also used in nuclear weapons, has a half-life on the order of hundreds of billions of years. Okay, so this is a very important property because it allows us to gauge just how persistent a particular radioactive material is going to be.